Well, by now you've already learned about Faraday's law of electromagnetic induction, and you can appreciate the equation we have here. It says that induced EMF, or voltage, is equal to negative the time rate of change of magnetic flux. The more rapidly magnetic flux changes, the greater voltage is induced. But we're going to focus now on what this negative sign is all about. I've stated earlier that that negative sign is a reminder to us of something known as Lenz's Law. So here's a demonstration on Lenz's Law that has to do with magnets falling through tubes. So here's the tube in this case. It's a piece of copper, and then we need to figure out which one of these two objects is a magnet. So I've got a paper clip to help me with that one. Nothing. This is just a piece of metal. Oh yeah, we found the magnet. Okay, so done with that paper clip. First, let's see what happens when we just drop a piece of metal through this copper tube. Now, fortunately, this copper tube has a little cutaway so we can see the motion, all right? And let's try this first. Let's just see what free fall produces, how much time it takes for this piece of metal to hit the deck when it falls freely. When I drop it through the tube, it's not quite going to be free fall because there might be a tiny bit of friction between the piece of metal and the walls of the tube, but you'll notice it's pretty close to free fall. Okay, so here's the really interesting one. Now I drop the magnet through the tube and watch what happens. Notice how slowly it falls. Finally comes through. Now, one more time. And it doesn't matter if I reverse the direction of the magnet. If it falls upside down this time, it still falls slowly. Doesn't make a difference. Now, why is this happening? Well, as the magnet falls through the tube, we can think of this tube as a bunch of rings all stacked on top of each other. And as the magnet approaches or falls away from any given ring, there's a change in magnetic flux that takes place. And that creates a voltage that drives current one way or another through each little ring segment. And for a moment then, these little rings, what we can maybe call the value of dl, right? If the total length of this tube is L, then each ring has a width of dl. And every one of those little rings with a width of dl, at the moment that the magnet is passing through it, has a current flowing through it. And that current will always flow in such a direction that the ring itself becomes a magnet that interacts with the falling magnet in a way to slow it down. And that's good. That keeps us from violating the law of conservation of energy. You can imagine if I took this thing and put it horizontally, if Lenz's law worked the other way, if Lenz's law said the falling magnet induces a voltage around the ring that makes the ring momentarily act like a magnet that pushes the magnet that's falling even faster, then wouldn't that be a trip if the magnet fell even faster than the piece of metal falls in free fall? That means I would be able to put something horizontally and give it just the tiniest little flick, and next thing you know, it could come out this end of here at tremendous speeds. There's no way around it. We're not going to violate the law of conservation of energy, whether we're working with magnets or any other type of device. So another way to think of Lenz's law is the idea is nature opposes any change in flux. Whenever a magnet moves in the presence of a coil of wire, currents are induced because of the induced voltage, and the currents are going to spiral one way or another through this coil, but they'll always flow in such a direction that makes a resistive force appear that slows or halts the motion between the magnet and the coil. It's sort of a self-defeating force that appears anytime we induce electric currents.